Today in this lecture we discuss about the position of the signals, means the chemical shift or shielding and de-shielding effect. The first topic is induced magnetic field. In the applied magnetic field, the valence electron around the nucleus are caused to circulate and they generate their own secondary magnetic field is known as induced magnetic field. The second topic is shielding. The circulation of electron around the proton itself generates field in such way it opposes the applied field. The field felt by the protons in thus diminished and the proton is said to be shielded and the absorption said to be upfield. Means when a molecule is placed in a magnetic field, its electrons are caused to circulate and thus they produce secondary magnetic field which is known as induced magnetic field. Rotation of electron about the proton itself generates a field in such a way that at the proton it opposes the applied field. So the proton is in shielded form. It is known as upfield. Next one is de-shielding. If the induced magnetic field reinforces and the applied magnetic field, then the field felt by the proton is augmented and the proton is to be de-shielded and the absorption is known as downfield. Means the rotation of electrons, especially for pi electrons, about the nearby nuclei generates a field that can either oppose or reinforce the applied field at the proton. If the induced field opposes the applied field, then proton is said to be shielded. But if the induced field reinforces the applied field, the proton feels a higher field strength and thus such a proton is said to be de-shielded. So, shielding shift and the absorption upfield and de-shielding shift the absorption downfield to get an effective field strength necessary for absorption. The compare with the naked proton, a shielded proton required higher applied field strength than the de-shielded proton. Shift in the position of N.M.R absorption arising from shielding and de-shielding by electron due to different chemical environment around proton are called the chemical shift. Generally, chemical shift measured from the signal of the reference standard such as trimethylsilane, which is known as TMS. The extent of shielding is represented in terms of shielding parameter alpha. When absorption occurs, the field, which is known as applied magnetic field H, felt by the proton is represented at as equal to H0 bracket 1 minus alpha is the first one, where H0 is applied field strength. Greater value of alpha, greater will be the value of applied strength which has to be applied to get the effective field required for the absorption and vice versa. Nu is equal to gamma H0 upon 2 pi, where this one is gamma H0 1 minus alpha upon 2 pi. It is clear that the proton with different electronic environment or with shielding parameters can be brought into resonance in two types. First one, the strength of external field is kept steady and the radio frequency is constantly varied. And the second one, the radio frequency is kept steady and the strength of the applied field is constantly varied. Clearly, at constant radio frequency, shielding shifts the absorption upfield in the molecule, where this is a spherical distribution of electrons around the protons. It is called positive shielding. Next one is reference standards. The character which are using for reference standards or chemical, first one is chemical inertness, Second one is magnetically neutral. Third, gives single sharp peak. Fourth one, easily recognizable peak. Next one, miscible with wide range of solvents. And the last one, it is volatile, means to facilitate recovery from the valuable samples. For reference standard, we are using the first one is trimethylsilane TMS. It is generally used as internal standard for measuring the position of 1H13C29Si in NMR. So, any proton or set of a proton which absorb at a field lower than TMS is given a positive value for del, means chemical shift. Trimethylsilane is the most convenient reference and has the following characteristics. The TMS at 0.5% concentration is used normally. TMS has 12 protons which are uniformly shielded because of highly electropositive nature of silicon at the center. Hence, the 12 protons gives single sharp peak at the value of del 0, which requires maximum magnetic field than protons of the most organic compounds. It is chemically inert, miscible with large number of solvents, and last one is highly volatile and easily removed to get back to the sample. Next one, it does not take part in intermolecular association with the sample and its all protons are magnetically equivalent. This is the trimethylsilane, the CS31, CS32, CS33 and CS34. All 12 hydrogen are magnetically equivalent or shows the single sharp peak. The value of del is 0. TMS can be used as an external reference also. The second one is sodium salt of 3-trimethyl propene sulfonate. It is a water soluble compound. It is used to internal standard for running PMR spectra of water soluble substance in the deuterium oxide solvent, means it is a water soluble compound. It is used as an internal standard for running PMR spectra of water soluble substance in deuterium oxide D2O solvents. Chemical shift is the difference between the absorption position of the sample proton and the absorption position of reference standard. This is variation of the position of N.M.R absorption due to the electronic shielding and de-shielding. Such shift compared with the standard reference in the position of N.M.R absorption, which arise due to the shielding and de-shielding of proton by the electrons, are called the chemical shift. For measuring of chemical shift of various proton in a molecule, the signal for TMS is taken as a reference. Due to low electronegativity of silicon, the shielding of equivalent proton in trimethylsilane is greater than the most of the organic compounds. Chemical shift measured in parts per million ppm. It is the ratio of shift downfeed from TMS, means hertz, to total spectrometer frequency megahertz. The chemical shift is independent of the operating frequency of the spectrometer. The value is vary from 60, 100, 200, 300, 400, 500, and the latest it's on 60 megahertz. Common scale used is the delta scale. Measurement of chemical shift. Each proton in a molecule has a slightly different chemical environment, has a slightly different amount of electronic shielding, which result in a slightly different resonance frequency. These difference in resonance frequency are very small. For example, the difference between the resonance frequency of the proton in chloromethane and fluoromethane is only 60 Hz, and the applied field is 1.41 Tesla. Since the radiation used in induced protons spin transition at the magnetic field strength is of frequency near 60 MHz, the difference between the chloro and fluoromethane represents a change in frequency of only slightly not more than the 1 ppm. It is very difficult to measure the exact resonance frequency to that precision. Hence, instead of measurement of the exact radio frequency of any proton, a reference compound is placed in the solution of the substance to be measured, and the resonance frequency of each proton in the sample is measured relative to the radio frequency or resonance frequency of the proton of the substance. The standard reference substance usually universally is TMS. The standard reference is also known as internal standard. The chemical shift formula, which is known symbol is del, which ppm, shift from TMS in hertz upon spectrometer frequency in megahertz multiplied by 10 to the power 6. For example, CS3Br protons chemical shift from TMS 162 Hz in 60 MHz instrument and 270 Hz in 100 MHz. So we calculate here the del value. The first one 160 upon 60 and the second one is 270 upon 100. The final value is 2.7 ppm. Hence, del value remains same in spectrometer. The chemical shift is measured in three major spectra: delta, tau, and hertz. From left to right, the shielding is in down field shielding, and from left to right it is up field shielding. The value varies from 0 to 10, and in the tau scale it changes to 0 to 10. In this table, the first one, the 1 ppm is equal to 60 Hz. So, this table in 60 Hz, and the second one is on 300 Hz. The values vary from 0 to 60 Hz, and this one the value is vary from 0 to 3000 Hz. This is the chart for different types of proton chemical shift value. The value varies from 0 to 10 and it is extended to 30, value of 30. The basic concept: the chemical shift or position of line in N.M.R spectrum gives information on molecular environment of the nuclei from which it arises. The chemical shift of nuclei in the different molecule are similar if the molecular magnetic environment are similar. The intensity of line gives directly the relative number of magnetically active nuclei undergoing the different chemical shift. The chemical shift is used for identification of functional group and as an aid in determining structural arrangement of the groups. Greater the shielding of proton, higher will be the value of delta. Greater is the shielding of proton, lower will be the value of delta. Electron withdrawing substituent like halogens, which deshielded the protons. Electron releasing substituent like alkyl group, which shielded the protons. The last one is the delta unit is independent of shield strength. Chemical shift position measured in Hertz are field dependent. Thank you very much.